Let's do the patient satisfaction example. So there's a data set available from Blackboard called patsat, and I've printed the observations. There's 46 observations with 4 variables. So the meaning of these variables is as follows. Y is going to be a patient's satisfaction level after visiting the hospital. We have 3 covariates that may predict satisfaction levels. The 3 covariates are x1 is the patient's age, x2 is going to be the severity of the illness. So some patients come in for very minor things, others can't come in for very major things. How does that link to satisfaction? The third predictor is going to be the patient's anxiety level. So how anxious was the patient during the visit? So then the question is, how do these 3 things relate to the satisfaction level? Well, the first thing that we should always do when we get a data set like this is look at the data. So if we just plot it, we'll get a scatter plot matrix, and what we'll see is that let's start out with the relationship with Y. So age has a negative relationship with satisfaction. So the older a patient is, the less satisfied that patient is with the visit. X2 was the severity of the illness, and this shows a similar negative relationship. The more severe the illness, the less satisfied the customer is, the patient is. X3 is the anxiety level. So the more anxious the patient, the less satisfied the patient is. Now we should also be on the lookout for confounding, and we see a lot of that. So what this scatter plot is showing is the relationship between age and severity. So older patients tend to have more severe illnesses than younger patients. Likewise, older patients tend to be a bit more anxious than younger patients. And there's a third relationship. The more severe the illness, the more anxious the patient is. So what we have are 3 predictor variables that are very correlated with each other, and basically they say older patients tend to have more severe illnesses and tend to be more anxious. Because of these correlations, we're going to have a hard time disentangling the individual effects. So if we do a correlation matrix of patsat, we're going to see the same thing. So fairly strong correlations among my 3 predictor variables. Each of them has a negative relationship with Y. Now, we're asked to obtain the analysis of variance table that decomposes the regression sums of squares associated with severity of illness, so x2, then with age given x2, then with anxiety given that the other 2 are in the model. This can be easily done if you fit your linear model in a special way. So all we're going to do is specify the variables in that order. So x2 comes in first, then x1, then x3. So let's go over to R, and I'll copy that in. And if I do an ANOVA unfit, we see exactly what was asked for in the course packet. So here is that analysis of variance table, and let's just interpret this. If we bring severity of illness in, so x2, we explain about 4860 in satisfaction. Now if we add to that age, we do an additional explaining of 3896. If we add the anxiety level, we do an additional explaining of 364. Now, just for contrast, let's estimate a slightly different model. So this different model will be y as a function of x1 plus x2 plus x3. And if we do an ANOVA on this fitted model, what you're going to note is that it's a little different. So we explain 8275 if we bring age in to a model that has only the intercept. Now if we add severity of illness, we only do an additional 480.9. One thing to note is the sum of these two, so if we just eyeball the sum, it's going to be roughly 8775, 8576. That's the same sum as if we add those two. You'll get this exact same number. It's just that, you know, with age alone we do a lot more explaining than with severity alone. But if you look at the combined model, you do the exact same explaining. Then finally, if we bring in the third term, which is anxiety level, you do the exact same amount of explaining. Now, just for comparison's sake, let's do a drop 1 of fit. And if I say test equals F, I'll get these F tests. And what you'll see is that the type 3 sums of squares for x3 are identical to those above. And this is just saying, you know, if you drop x3 from a model, leaving x1 and x2 in, you lose 364. We can think about this as saying if you add x3 to a model that already has x1 and x2 in it, you do an additional 364 of explaining. Notice the F test gives you exact same p-value, 0.06468. Now if I do a drop 1 of fit 2, you will get exactly the same sums of squares. So notice that if you drop x2 you lose 81, if you drop x2 you lose 81. So these partial sums of squares don't change depending on the order of the terms. The extra sums of squares do change. Now let's go on. So test whether x3 can be dropped from a regression model given that x1 and x2 are retained. This test is very easy in R, and with all 4 of these drop 1 or ANOVA results, we get exactly the same p-value. So the p-value is 0.064 regardless, and our conclusion is that we really don't need x3. So if x3 were equal to 0, then the additional explaining is just not significant. It's entirely plausible that we would observe a coefficient that is well, let's bring up the summary of it. Summary of fit. If x3 were indeed 0, the chance that we would observe a regression coefficient this extreme or more extreme would happen often enough, so about 6.5% of the time. Therefore, we can't reject the null hypothesis that x3 is 0. So we could potentially drop that term. Notice that we get the same result with the t-test, and that's not an accident. So we get exactly the same result with the t-test as we do with these partial F tests, dropping 1 term at a time. Let's move on. So the next question says, test whether x2 and x3 can both be dropped from a regression model if we retain age. So do we need both of these terms if we have age in the model? So what we're really testing is the null hypothesis that both beta 2 and beta 3 are 0. This one's a little bit more complicated. So I'm going to fit a new model, and let's call this, we'll just call this fit 2 as well. So fit 2 is going to be an LM of y tilde x1. And so fit 2 now is a model with just x1 in it. So this is the reduced model. Under the null, beta 2 and beta 3 are constrained to be 0. And well, beta 2 and beta 3 are not in this model, so those coefficients have been constrained to 0. Now, the simplest way to actually do this test is to use a function called deviance. So let's go back and look at an ANOVA table for fit 1. What this says is that 4,248 was left unexplained by a model with all 3 terms in it. the deviance of fit gives you only that number. Now let's look at an ANOVA table for fit 2. What this is saying is that we've left 5093 unexplained by using only x1. So if I do a deviance of fit 2, we see that that's what we get, 5093. So if I take the difference of the deviances, so fit 2 less fit 1, this tells us the additional explaining that is done by those two terms, by adding x2 and x3. Now if we go back up and look at one of my previous ANOVA terms, so in this model, what I did was I added x2 then x3. The sum of these two terms tells us what happens when I bring x2 and x3 in. So I can just eyeball this, and it's about 845. And notice what I got down here, 845. So that's the amount of additional explaining done by adding x2 and x3 to a model that only has x1 in it. Now we need to do the f-test. So how do I do that f-test? If we go back, I'm going to take the extra sums of squares, that's what we just found, and divide it by 2. So let's do that. So if I take this and divide by 2, we get the numerator of that result. Now let's go back and look at the fit. This is going to be the denominator, 101.2. So let's go add that to this. If I divide this by 101.2, this is an F statistic. So if we go back to the course packet, I've just kind of illustrated everything I just said, and there is that 4.17. This is an F distribution with 2 and 42 degrees of freedom. The 42 is coming from here. The 2 comes from the fact that we're deleting 2 variables or adding 2 constraints to this. So if I take this whole result, let's take 1 minus PF, that's going to give me the area under this F distribution with 2 and 42 degrees of freedom. My p-value is 0.022. Now here I think I asked you, or the book had asked you to use a type 1 error rate of 0.025. This is less than that, so we can reject H0 and conclude that both of these are not simultaneously equal to 0. So I'm going to need at least one of these two predictors in the model. Part 3 is a little bit more challenging, and I only teach this in when there's as time permits. So I'm not going to require you to know how to do this more advanced test. That's it for using this general linear hypothesis